around what engineering actually means when we're looking at it from a digital product development perspective, right? So I think a lot of you would be working on some form of tech product or that has some form of software solution behind it. And what we want to do today is give you information to be able to ask the right questions. But I won't tell you everything up front. I will jump through to give you all the information at the end, I believe. So a little bit about myself and my colleague. So I'm Etienne Smith. I'm CTO at Mohara. I've also been a CTO and advisor for multiple ventures and startups over my career, and very much worked on scaling these ventures up. So I've scaled quite a few ventures from the pre-seed stage, which is very much where you guys are, up to Series B+. And that's a very exciting journey. So Tom, I don't know if you want to quickly introduce yourself to me. You're on mute, Tom.
Yeah, as Ed said earlier, this is my first Zoom meeting ever. Sorry, guys. Definitely not. I'm Thomas Mundell. I work under Etienne at Mohara as a software engineer, and I've principally worked on projects in the fintech and green tech space. And I previously worked on embedded systems and electronics and hardware design. And prior to that, I studied electromechanical engineering at university.
Cool. Yeah, thanks, Tom. So as LJ very kindly said, it's a little bit about Mohara. So we're a global product and venture building business. We focus at ventures or startups when we're working with them in the seed to Series A stage. So it's very much about growth and understanding what a product looks like at the start with, developing product market fit. So we're around 70 people across 5 different locations. So lots of these kinds of remote calls. So Tom is actually dialing in from Cape Town today. And then we've partnered with multiple businesses, more than 30 over the years, looking at the types of ventures and products that you may be building yourself. So what we're going to run through today, I'm going to give a brief introduction, just to explain a little bit about the purpose of it is, like what do we want to try to gain out of that. Tom will then run us through the intricacies and complexities of what software is, where I'll go into a little bit about computing, and how software and computing combine to build applications. And that's very much, if you're looking at digital products, they're always going to be application-based one way or another. And then Tom would like to run through just like the mechanics of software engineering. Because again, as LJ said, it's important to know and understand the people that you work with. And software engineering has a lot of principles and practices that there's buzzwords for you to learn, but also to understand and learn more about. So quick introduction. So I hope everybody in this call is looking to be a leader of a business at some point in time. And so for a leader of a technical business, it's really important to understand the kind of work your people will do. It's to get that bare minimum behind how modern technology works, and put that together, to string together the complexities of your systems. So it's impossible to learn everything, right? It's a massive topic. I just said this to LJ. I've done lots of these types of presentations, some internally that have run for hours. But as a business leader, it's important to be able to ask the right questions. And that's what we want to try to get or give to you today is a base level of understanding so you can ask the right questions. The tricky piece is that the evolution of technology is rapid, right? So if you don't stay on top of it and continuously come back, you're going to struggle to be able to communicate down the line. A good example of this is that 10 years ago, machine learning wasn't really possible. It was possible, but it wasn't accessible at least. And this means that, with the development of how things have changed, if you hadn't stayed on top of that, you would have effectively missed out on something that your business could have leveraged. So we're going to follow through a little bit of the basics behind this. This presentation is an engineering 101. But I'm sure there'll be lots of questions at the end. And as LJ said, either pop them in the chat or we can have a little Q&A session. Without further ado, I'd like to hand over to Tom so he can discuss a little bit around, what software is and how it all pieces together. So over to you, Tom.
Thanks so much, Ed. So I'm going to do my best to briefly summarize what software is in a nutshell. I'm sure we can all understand that it's, extremely broad field that's been around for quite a long time with a very rich history and lots of interesting stories. But today I'd just like to give you some insight into, what I think are the most important things to understand about software. So software is what allows humans to interact with computers, whether that's interacting with the software products that make our lives so much easier, or actually designing and developing these pieces of software. It's the tools we use to it's all the tools we use to communicate with computers. And the history of how humans have achieved this is long and full of interesting stories, as I said. What I have to do is just provide a little explanation of what is at its core. So computers are machines made of transistors. And these are very small switches that can be turned off and on again billions of times a second. And in your modern day CPU that you'll find in most mobile devices and laptops and personal computers, there's billions of transistors in the CPU and the little piece of technology that is that big. So computers can do certain things many times faster than humans. And I'm not going to go into why that's useful. I think we can all gauge that. And programming languages define sets of instructions that computers can interpret. And with software, what we're essentially doing is giving the computers commands. Software allows us to string these commands together logically, precisely, and unambiguously in a language that we can read as a group of people collaborating on a project, that can then be translated into zeros and ones, which is practically the only language that machines can read and understand. And the machines can't get confused. They have to have these instructions in a very particular way. And if they get confused, you'll get the classic blue screen of death, and things will just error out. So programming languages have been around since the 60s. Some of them that were invented back then are still in use today, and there have been many new ones developed over the years. Our use cases for programming languages have rapidly expanded as to what they were 50 years ago. There's billions of people around the world with cellular devices and computing devices that use them to shop, eat, communicate, and do so many everyday things. And new programming languages have come about to provide us with more useful and more efficient tools for creating these products. And so as a software user in 2020, what you're doing is you're interacting with the top layer of the software stack, which goes down quite a few layers to eventually end up at those tiny little switches, those transistors that I mentioned. So at the top, you have your application layer, which would be your Instagram and Facebook and whatever apps you have. And in the context of a mobile device, you'll have an operating system such as iOS or Android that these applications run on top of. Similarly, with a laptop or a PC, you'll have your Mac OS or Windows that run underneath the applications, or a Linux distribution if you're that way inclined. And so the operating system then deals with these applications. It deals with the sort of output that they create. And if it needs to go down to the hardware, then it does. And it has a way of translating the sort of, if you click your mouse on a button or on some part of your screen that's supposed to do something, that communication will be filtered down to the hardware, and some computation will happen, and then it'll come all the way back up, and you'll see your menu open, or whatever action, the output of whatever action you took. And so depending on what device you use, there may be, 1, 2, 3, 4, 5 layers. It's usually quite a lot with a mobile device or a PC, but even if we think of like a dishwasher, you have little buttons that you press, your controls, and you have a little LED screen, and there'll be some code that runs on the computer in your dishwasher, and that's just one layer, that deals straight with the machines. But there still is computation that takes place to interpret your commands and turn on the engines and actually do something. And I'm going to now hand over to Etienne, who will.
Thanks, Tom. Yeah, I think it's interesting because, as Tom mentioned, your software can run on anything, but what runs it is actually the piece that is known as computing, right, or compute. So it's important to know that the base of all computing is computers. That's a nice, friendly terminology for it, but we often also call it hardware. And as I mentioned, all software runs on some kind of hardware, no matter where it is. So that could be a PC, a mobile device. What we'll touch on a little bit later is, cloud servers and cloud infrastructure. And as Tom mentioned, like hardware is controlled by switching these nanoscale transistors. They're really tiny, with binary fields or binary values, right? So zeros and ones. So when you set these zeros and ones, right, they're received as an input. It changes a state in the system, a physical state in the system, and will return some form of output, but in the same format. So to do this compute, we need that hardware that processes the data, but equally as importantly, we need the hardware that stores the data. And a good way of thinking of that is like the RAM you have on your mobile device or your hard drive on your computer. You're still having a computer that sets physical, binary fields for that. So how much data we can store, how quickly it can be accessed, but also the compute constraints around that define what we can do with software. And a good example of that is, as I mentioned earlier, we look at machine learning. The fundamental change with things over time has meant that with machine learning as it is right now, we're able to run it in cloud servers, cloud compute, which can scale infinitely, theoretically. So as I mentioned, cloud computing allows all of this work to be done remotely, but equally as important at scale. So in the past, you used to have a physical computer or a PC or a server that sat inside your office that stored your Outlook emails or your files. But this distributed computing means that applications can scale, right? So it means that you can run multiple servers in multiple locations all over the world. And this means also that you can deliver that compute when and where you need it. And the where is equally as important as the when, because if you had a server sitting in Los Angeles and you're trying to run Instagram in the Philippines, you're going to have a lot of problems with that, and the application will not be user-friendly. So there are three major cloud service providers out there today. There's lots of other people or other businesses that plug into it, but the major services are Amazon Web Services, Google Cloud Platform, and Microsoft Azure. And these provide these massive server warehouses that are distributed globally. And it means that you can run compute resources on demand, and customers only need to pay for what they use. So you don't buy a big server just in case. You can scale for just in case. And this means you reduce cost risks, operational risks, and it has much smaller barriers to entry. So the kinds of services that those platforms provide can go from a compute server, which is just a CPU that does operations, to a database server, or somewhere where you can store your files remotely, your cool Instagram images. But just as important is it actually also bakes in security. So the security is managed within the cloud, and the security is updated there. And that means that your risks of operating your business are reduced. Furthermore, it actually provides close to 100% uptime. And as I've mentioned many times already, some global availability. And that's the combination of all those things within cloud compute has changed the way the world operates. It's allowed the likes of Facebook and iOS and the App Store to grow as it has. So that leads relatively nicely into what is an application, because when you start combining the software that Tom mentioned and the compute hardware that we just discussed, you end up with an application, right? So they're the products that combine those two things together. And so without the compute resources or the code that is built with the software, you don't end up with an application. And the applications can run these days anywhere. Like as we know it, they run on your mobile or in browser, how we're accessing the Zoom call potentially. But interestingly, it can also be behind the scenes. So the routing of calls in a call center is an application. It doesn't necessarily have a user interface, but that application is running on a server, it receives data, and it transfers data. So the software that runs an application is generally what we define within two components, a front end to the software and a back end to the software. So the front end is the piece that you as a user or consumer, you interact with. You click buttons, you save files, you upload images. The back end is the piece of the software or the piece of the application that controls the business logic and controls the data and knows where to store those images or retrieve those images, as an example. There's another way of looking at this front-end, back-end view, and that's the client-server model. With the client being the front end, the piece that you interact with, your browser or your mobile phone, and the back end being the cloud compute server, where you send your chat messages through WhatsApp. It goes to a server and then sends it back to another client. There are cases where you have an offline desktop app where the client and the server are bundled together. So Excel is a fantastic example of that. But generally, the web applications and mobile applications we're used to uses the client as your browser or your mobile device as your client. And then the server is run in a distributed cloud computing environment. So how do these two pieces communicate? So there's a word you probably have heard many times in life, or at least an acronym, API, which stands for Application Programming Interface. That is the comms layer between the front end, the back end, the client, and the server. And it's a really important concept to understand, because an API defines how they communicate with each other. But it can be leveraged in many other ways too. The API can also allow for external third parties to communicate with your application. So we often build an API that we expose to other companies to make payments, send orders through, retrieve data, etc. But then there's the other side of the scale where you have third-party APIs you may integrate with. A really good example of or some good examples of these would be Stripe. So Stripe has an API to process a payment through a card gateway. So it has a back-end API that actually processes the payment, but it can also actually has a render or generate a front-end for you, and that's also API-based. Similarly, there's a company called Twilio that does loads of SMS automation through API, or you can even send out WhatsApp messages, Facebook messages, etc. And then one, well, if you've listened to as many podcasts as many people do, you would have heard of MailChimp. So MailChimp has an API attached here too, where you can automate your email, your emails that you send, or the content that goes in it. So it's really important to understand that APIs are one of the central foundations within modern applications, both for other third parties to work with you, as well as for you to integrate with their systems or solutions. One other important piece to understand around applications is the utilization of frameworks. So frameworks are it's a concept that's software programming language based. So it's a way to leverage a language in ways that it may not have initially been designed for, or to make it simpler for developers to use it. So in the right there of the screen, you can see there's two logos effectively of two frameworks. The one is called Node.js. So Node is a framework that works on JavaScript, which is a program language, but it optimizes JavaScript for backend use or for server use. The other little logo there that looks like is called React. And that is a front-end framework that also is based on JavaScript, but it optimizes JavaScript to build front-end views, user interfaces, and the interactions that you work with. But just as similar as there are many frameworks and languages that are optimized for a specific use case, it's quite important to also understand that there isn't just one type of data storage or database type. There's actually, well, several, many database types, but two that are important that you will likely hear through your career or while you're doing your business is a relational and document database. So the relational database is the one we all innately understand. It's a table or an Excel spreadsheet. It's all based around rows and columns, right? The two-dimensional view of data. Whereas a document database is an interesting concept because it's no longer just two-dimensional. You can store your data in an object, and it can have nested data that links quite deeply through. And they both have different use cases and purposes. And so when you're talking to a team or when you're designing a system, it's also good to look at how do I store my data and in what format. So that decision around how do I store my data and in what format falls very neatly into what software engineering uses or what software engineering defines as the optimal way to do these things. And for that piece, I'd like to bring Tom back in just to chat through software engineering in a little bit more detail.
Thanks so much, Ed. So software engineering is essentially what ties together all the things we've discussed into organizational processes that give us products that are ready for the market. And to ensure that software has been developed to create a product that gives users the experience that the business actually wants to give them. The image in the previous slide is what you wouldn't want a software team to be doing just after a new feature has been released to users. Looking all panicked and like they don't know what's going on and what have you. And following software engineering processes, principles, and standards is how we mitigate that risk. And of course, this starts off with the initial design of a system, where a suitable software architecture and design principles need to be selected. And this, of course, depends on the type of product that is being designed. There are trade-offs to every architecture or every way of designing something. And the context of the problem will inform the trade-offs which need to be considered the most when actually selecting the design that you want to select and move forward with. And in the image, you can see two examples of commonly used architectures. On the left is a monolithic architecture, and on the right is a microservice architecture. And both of these architectures can be employed in different situations where in one case, one might work better, and in another case, the other might work better. So in a monolithic architecture, all functionality is centralized, sometimes usually all on the same server. And it can be simpler to write and deploy to actually release for users to use because it's all in one place. But if the system starts to get more complicated and more pieces of code get added on to add more features and to update the system, and just when functionality becomes more complicated, it can be harder to add things on because one change will impact the entire system. Adding one piece of code could break one thing, and then that thing could break something else, and it's all together. It's all very tightly coupled. And with microservice architectures, it's different in the sense that each part of the system which creates a particular kind of functionality runs on its own service. So each service will run on its own server. So it's all the functionality is distributed between each of these services, and each one does a very particular thing and then communicates with the rest of the services. So with our monolithic architecture, you can see that the UI, business logic, and data access layer, which is the part of the program that would interact with the databases, that's all in one spot. Whereas with a microservice architecture, you might have one service, which is the software that creates the front end, the user interface, the user experience, and then that service will communicate with another service which does some business logic. And there might be many servers which deal with business logic and all chat to each other, and then chat to another microservice which accesses the database, finds information, and then sends it through to business logic service, and then maybe all the way back to the front-end service. And this can be, of course, more complicated to set up than a monolithic architecture, but it allows updates to be more atomic and granular in the sense that, if you want to just change something with one service, you're just interacting with one server. And if something doesn't work, then, it's just one service that's broken, and that might not affect the entire system. Sometimes it does, but you'll try and design it not to. And having that separation of concerns can be very useful, but sometimes isn't the right way to design something. And then once you've developed your system, and to ensure that, things actually work as you want them to with each release, features and the software needs to be tested before they're released to users. And testing software is a very big topic, but I'll just briefly describe different layers of testing that you can use to ensure that, your users are using software that works and isn't buggy and, it does what it's supposed to do. So our first layer would be unit testing. And those are tests which are designed to test small pieces of code. So in a microservice, you might have lots of different little pieces of code, and then corresponding to those individual units, you'll have unit tests that test each specific unit. And then our next layer would be our integration tests. So whereas the unit tests test everything inside a service, the integration test will test that the services actually communicate properly. And when one service gets a predefined input, it creates an output that the other service expects. And in the sense of a monolithic architecture, you'd be checking that your server can communicate with your front end, and that you're getting the inputs and outputs that you expect. And so that's testing software. And then the next layer, you'd want to have an actual person testing your code, sending outputs, making sure that they're getting the right inputs. Sending inputs and making sure that the code's producing the right outputs, and then actually, using the product. So once QA is passed, once you've had your quality assurance, you'll actually want, third parties, maybe actual users, to test your software. And then, if they spot something that's different than what it originally was, they'll, deliver a report and give you some feedback on how your new feature is working. So in our software development lifecycle, it'll start off with, your minimum viable product or your first release. And then, as features and updates are added, the business will get bigger, and you might get to the stage where you're releasing hundreds of updates a day. And, of course, the amount of updates you need to release, or the amount of features you release, will depend on the scale of the application. But yeah, we need some tools and processes to manage those releases and, manage the life cycle of the project. And DevOps tools and processes, which involve CI/CD, which stands for continuous integration and continuous development, are designed to increase the efficiency and safety of these releases, in the sense that you don't want things to break when you release new code. So continuous integration means that you're constantly releasing new features, instead of once per month you have this huge piece of code that you add. And it's preferable, because if you're adding thousands and thousands of lines as an update to a piece of software, if something breaks, then you have so much more to look through to find the problem. Whereas if you're doing very small incremental changes day by day, if something breaks, you can just roll things back, and then hopefully they'll work like they did before. And a version control system is something that helps us roll things back. So every time a new feature is released, the version of the software will be incremented. And so if we have, each of those, every single version versioned, then we can kind of have a tree and a history of what our software project looked like. And a very, very popular tool we use to do this is called Git. It's actually the only version control tool I've ever used. And it allows us to actually go down to the line of code, see the letters and numbers that may have changed, or the symbols that may have changed in a particular line. So it allows us to have very stringent control of what is added and what is removed to our software repository, which is extremely useful and actually like vital. It's essential. You can't really do software engineering without it, in my opinion. And then, of course, over the life cycle of a software project, security needs to be under constant consideration. When you're developing a system, you're going to try and protect it from as many different types of attacks as possible. You're going to try and limit the amount of vulnerabilities in the system, or obviously make sure there are none, or just try and manage them. And all it takes is for an attacker to find one vulnerability. As a developer or engineer, you're trying to protect against so many things, but at the end of the day, all they need is one. And it's just something that has to be always considered. And a way of testing your system, making sure that it's secure, is to employ penetration testers, which could be an individual or could be a company, to actually try and hack your system and test if there are any vulnerabilities, and at the end of the process deliver some kind of report, which will tell you whether they were able to get into your system or extract some data, and that'll just allow you to assess whether your product is secure. And then a discussion of software engineering wouldn't be complete without a little word on documentation. So in my personal view, it's always absolutely vital to include a little user manual on every piece of code that you've written. This allows new members to be onboarded onto your team very easily. If something bad happens, then you have a sort of document explaining what went wrong, which is way more efficient to explain to a huge group of people. I mean, if something bad happens, you're going to want to get as many engineers in the problem as possible. And to have a clear, concise document is sometimes, I think, much better than having a Zoom chat, which will initially happen. But yeah, so that's a small word in software engineering, and I'll give it off to Ed.
Yeah, thanks, Tom. It's always tricky, like I said at the top of this, this whole piece around application development, software engineering, computers, hardware. People spend their entire lifetimes learning about this. And so it's impossible to know it all. What we try to do is go and give you a taste of all the different aspects around developing an application or developing a product. And I hope that there are quite a few questions for you to come out of this. Like, I generally find there's quite a few that pop through. LJ, you mentioned the chat. Shall I stop sharing or bring the chat up?
Brilliant. That was so interesting. Even I understood it. So that is a great point. Maximilian, I've just seen in the chat box. Yes, absolutely. We're recording it, so I will send that over to you when it's been edited. Just a chance now. Thanks, guys. That was absolutely awesome. Great presentation. Really, really helpful. Just time for you guys to ask any questions you've got, any clarifications, because it was a whistle stop through Engineering 101.
Very much so.
Either shout it out or just pop it in the chat box. Either way is absolutely fine.
So while we wait, I think it's good to give some more context and clarity around one of the key pieces that I mentioned. We spoke a little bit around databases and why there are different types of databases. So similar to languages that we have these days, we have languages like C, which is very close to the hardware and means that you can physically manipulate or manage the hardware. You can start working with different types of databases, particularly for scale. So you might have heard about big data or different types of big data solutions. And they all require their own type of language or database all in one go. Sorry, I've now jumped ahead and not given an opportunity for questions. I will mute.
I think you run the risk of just being too clear, guys. Anyone got any final questions or thoughts? Etienne, if you then want to continue with your point, that's absolutely fine.
Fantastic, I will do. So I think one of the key pieces when you are trying to design a system, so let me get my video back on. As Tom mentioned, that there's a bunch of different architecture types or ways to architect an application. And when you're working with your team, when you're starting with your team, it's important to understand the kinds of risks that you're trying to mitigate over time. So if you're focusing on trying to build something that's simplistic, where the code is all bundled together, a monolithic architecture is quite valuable because your developers are all working on the same system in one go. The problem with that is when you get to a certain scale or size, you get to a risky scenario with monolithic architectures. So the first people that initiated the microservice or made it popular with the microservice architecture was actually Google. And the reason why they did it was they knew there was a centralized risk in keeping all of their code and all of them, like the interactions of their code, in one big service. So they decided to split it up into functional pieces that can do a very specific job and grow and scale at that job. So a good example of that would be an email automation tool, or maybe let's use a tangible tool. So Google Sheets is running on a completely different service to Google Docs. And that means that were the load of the compute required for Google Sheets to grow or increase, or if something was to go wrong, Google Docs would not fail. Or were it to be your Gmail or calendar application within G Suite, they run completely independently. And they actually also have independent databases. That's the other really interesting thing around separating out these microservices, is that you're able to choose the language and the database that is applicable for your objective. So I'll give you an example of a project we're currently working on, which is a fintech. We have at the moment around 40 different services that are running for it, each independent with its own database, doing its own job, from sending out an email to sending out a text message to doing some complicated data computations. And it means that we can scale the system completely independently, but we can also release updates without risking the rest of the system. Yeah, so I find it a fascinating topic. Maybe it's because I'm a CTO, and maybe because I am a nerd, as the lead into this chat mentioned. But trying to understand how your product is built together is a really important piece from a business leadership perspective, because it defines the risks that you have moving forward, or your ability to grow. And so it's an important question to push your CTO or your architect or your developers on, so that they understand how that system will grow and scale. I wonder if there are any questions from your side, LJ or Matt, for that matter.
I mean, I guess one of the questions that comes up quite often with our students is actually kind of how important is it to bring on someone who has these skills? I mean, how much, if you're building an app, for example, how much do you think you can do by yourself if you have no tech skills and you've done a very useful course like this? Do you think it's possible to go about that, or do you think it's always better to work alongside someone in the know?
Yeah, that's a brilliant question, LJ, because I think it's something that's going to be covered later on in the series. But I think that's maybe one of the tricky bits around what we're doing today. I don't think the information that we're giving today is for you to start with. It's for when you need to grow or bring in your team. It is completely possible to build a business without any technical knowledge. In fact, we see it quite often. And there are loads of process automation and third-party tools and no-code, as I think there's a talk on no-code solutions for a non-technical person to build a product with. I think the piece of the information that we're trying to give today is that always has a limitation. You can only go so far before you need to have a robust, scalable solution, right? And that's when you start recruiting a CTO, and you want to know, what do they need to know? What are the important questions to ask the CTO? Or when you start recruiting your first dev team. So if you're completely non-technical, it's important to be able to ask the questions around, how do they work? What do they currently know about building solutions? Because it gives you information on their knowledge, experience, capability, etc. And then longer term, you know, the kinds of things we covered in the chat today, they effectively help you manage your business day to day. Like, it's an operational piece too. So I would not take the talk from today as a recipe on, you know, what you need to know today to build a business, but it's what you need to know to scale and grow a business. That answers your question.